Hello, this is Mohit from IIT Madras and I will be presenting our work on real-time restoration of dark stereo images. Stereo imaging has a lot of real-world applications ranging from autonomous driving to virtual reality. But unfortunately, most of the advancement in stereo imaging has been done for well-lit conditions which cannot be leveraged for extremely dark conditions such as late-night scenes. In this work, we thus aim to restore the perceptual quality of extremely dark stereo images as shown on the screen in a way that the restoration process obeys the epipolar constraints for downstream applications. The basic idea is that the inference network responsible for image restoration will use only 2D convolutions, but during the training phase, it will be trained using a epipole preserving loss function. Our solution thus consists of a hybrid unit architecture and a depth-aware loss module. The hybrid network processes the left and the right views independently in the initial scale spaces due to the large disparity. However, as the scale spaces become finer and finer, the network receptive field increases but the view disparity decreases, and we thus process the left and the right views jointly to save time and memory. For example, in the Kitty dataset, the maximum view disparity is 256 and so at 1 by 8th resolution it reduces to 32. But our network's receptive field right after the first convolution at this scale space is at least 36 cross 36. Our depth-aware loss module is inspired from classical computer vision techniques, but it additionally allows backpropagation to train neural networks. Since our loss module is based on classical methods, it can be used out of the box to train any neural network for arbitrary stereo settings. Our loss module in essence searches for pixel correspondences between the left and the right views by using normalized patch correlation. But we found that this step is compute heavy and realized that more than the patch size, it's the context which is more important. We thus introduced a dilation term to reduce the complexity, and please refer the paper for details. We additionally impose some constraints like the disparity with respect to the left image is always negative and exploit the knowledge of maximum disparity if available. To simulate low light conditions, we do not resort to simple but inaccurate ways such as adding Gaussian noise, but study the physics of different stages of image acquisition like the photon arrival, electron generation, and digitization using the ADC circuit. We thus use a heteroscedastic Gaussian noise to simulate low light conditions for benchmarking. Qualitatively, we find that our restorations are better than existing methods both visually and geometrically. With that said, even our method struggles when situations are pretty dark. We even collected some real midnight images to test our network with machine vision cameras mounted on a stereo rig as shown on the screen. The screen further shows few example scenes. We find that even for real dark scenes, our strategy works well for both visual restoration and downstream depth estimation. These qualitative results are also backed by quantitative results. But what is more important is that our network achieves this with 10 to 100x lower floating point operations and 4 to 30x speed up. Thank you.